All right, good afternoon, everyone. Welcome back for our final session of this year's showcase. I'm Stephanie Seaman. I'm an electrophysiologist here at the Institute. For our final team talk, we're going to hear about how the informatics team takes on the challenges and best practices involved in generating and maintaining an organized code base that allows all of the experiments and the data analysis that goes into our large-scale pipelines run smoothly. Representing the team today is Niall Gratis, Nick Kane, Jed Perkins, and Nika Keller. Please join me in welcoming them.
Well, thank you very much for that introduction, Stephanie. My name is Nicholas Kane, and it's a tremendous pleasure today to be speaking with you all and be sharing the stage with Niall, Jed, and Nika. We're really excited today to tell you about how we build trustworthy informatics pipelines and how that's a really big team effort. It's not just a team effort within the technology or informatics teams, it's also a team effort that extends beyond those borders to the research scientists, to the engineers, and beyond to make sure that our data is as impactful as possible. So what I want to highlight is that there's a common theme among all of the pieces that we'll be presenting today, and that's how software engineering culture that we all try to espouse and practice can facilitate through our interactions with our research science colleagues, the type of data science that we're trying to do here. So I'll be first speaking about the MTrain service, which is really, I'm hoping to highlight how this is a tool that can aid in the cross-team collaboration in engineering. Then we'll also be hearing about how some of the tools in communication in software engineering can help collaborative coding and stabilize code bases, especially as we move into testing and making sure that our pipelines work consistently as they're being modified by the research scientists. And finally, we'll be talking about how AWS and cloud services can really extend our reach by providing consistent access to all of our tools and all of our data and make our data more impactful. So I'll begin by talking about the MTrain service. There's a lot of friendly faces for me in the audience today, but a lot of new ones too. And if you've heard me talk around the water cooler or the coffee machine, you've probably heard me say MTrain, but I've never really presented publicly about what that service is. So essentially it's a software system that coordinates the training during a change detection task. I won't go into details about the change detection task, but the major components are that a series of flash stimuli are shown to the animal, and then the report of a stimulus change has to be reported by a lick to a lick spout. Now, these animals don't perform this behavior innately. They have to be trained to do this. Several weeks of training go into getting an animal ready to perform this task. And MTrain is the service that coordinates that training. You can think of it kind of like elementary school, but for mice. So they start out at kindergarten, and they can't progress through the different stages of their education, if you like, until they perform at a certain criteria level. So this is a schematic of this, and if you're familiar with the concept of a state machine, it's a state machine that allows animals to progress according to certain criteria through the different phases of training. Sometimes if an animal needs to go back for sort of remedial education, it can follow one of these edges back, but eventually it reaches to it performs at a certain level so that it can partake in the imaging portion of the experiment. And the MTrain service really tries to encapsulate this training procedure, and we call this a regimen, and it essentially encapsulates a workflow, but MTrain can hold multiple regimens simultaneously at once. And so mice progress through on one regimen, but can be migrated from one training sequence to another. And the stages don't necessarily have to line up for this to happen, although some level of intervention has to happen to say if one animal has to move from a regimen to another. You can think of it as kind of like moving from, changing cities and having to go to a different type of schooling system. So these can be customized for particular genetically modified mice, or if the needs of the research scientists change and we decide that the regimens have to have tighter control over when an animal can progress between stages, that requires or necessitates the redefinition of a new regimen. Simultaneously, if there are bugs that are found in the software systems that actually implement these procedures, those can also be repaired or replaced by progressing the regimens. So the service holds on to the full history of these regimens in order to coordinate these training systems. So this is illustrated by this table here. I have several different subjects noted 0, 1, and 2, and MTrain holds internally a whole database that it uses to decide when the animal can progress according to a performance metric, D prime, and holds full data provenance associated with which animal performed on what date, under which series of parameters, and at what level of training. And this allows, at the end of the experiment, to have full access to the history for each animal's configuration. I want to underscore this because this is really solving a critical operational need in the collaborative work that we do as an institute. So there's many different parts of the institute that go into coordinating this system. Obviously, the research science is critical in order to define the training stages that have to be executed. Myself and my collaborators in the technology team assist in this sort of software engineering. The manufacturing engineering works to create the software that actually implements the training on the rigs, and of course the neurosurgery and behavior teams that train the animals, and the IT operations team that actually supports the software as it runs in the institute. All of these teams have collaborate to make sure that this system operates according to all the different needs of all the different actors. And I think I want to leave you with this high-level point that there's a dynamic interaction, especially between the research scientists and the engineering. Science necessitates flexibility. You have to be able to redefine as you take in more information about what needs to be done to design your experiments. We have to be flexible and accommodate those needs. But one thing that I've learned working in the software engineering teams is that engineering requires stability. If we're going to know, we need to be able to track the full history of the training for every animal. And these two needs are oftentimes in tension with each other. If you've ever worked and done a version or a draft of a paper or an analysis and then had to copy and paste that in your directory structure in order to save the history of what you did, but progress it multiple times as you refine your experiment and your thinking, then you probably know exactly what I'm talking about. So this dynamic interaction among lots of different teams is what this service tries to support. So that's an example of how collaboration is aided by some of the work that we do in the technology team. Next, I'm going to hand the mic over to Niall, who's going to talk about how software engineering communication strategies can aid in the coordination of our team's efforts.
Hi, my name is Niall Gredis, and I'm going to talk about some fundamentals of collaborative software development. So, modern software projects can get really large, and that's no surprise. It takes a lot of work in order to build something impactful. And while having many contributors makes this work lighter, it also adds a new layer of coordination problems. And that's true whether your project has 10 or 30 or 1,700 developers. Communication is the best tool that we have for solving these coordination challenges. It's not easy, though, and if we don't do it right, we are likely to end up with some characteristic problems, which I'll run through in a moment. For one thing, when developers work alone, we're likely to write code that only we understand. If my collaborators or myself in a year can't easily tell what my code is for or how it works, they're going to have a hard time debugging it or adding new features to it. This wastes their time, and it makes us likely to add new bugs whenever we try to introduce changes. Not only that, but if we're not working together on a common code base, there's a pretty good chance that we're going to end up reinventing wheels. This is also not a good use of our time, and it can lead to heartache when implementations that ought to be the same actually behave slightly differently under certain edge conditions. So how do we solve these problems? What we need are more eyes on the code that we write so that our collaborators can tell us when our work is buggy or incomprehensible or has already been written. And we can get these eyes by building a review into our workflow. With modern tooling, this is actually pretty slick, and I'll run through an example of how we develop for the AllenSDK using such a workflow. What is the AllenSDK? It's a Python library, an open source Python library with tools for accessing and using some of our data, as well as some of the code that runs in our production pipelines. You can find out more at allensdk.readthedocs.io or by finding us on GitHub. Okay, so the master copy of the AllenSDK, which is where we want our work to eventually end up, and our work here might be a bug fix or a new feature. This lives on GitHub under the Allen Institute organization. So the first thing that we need to do is to pull it down to our local machine where we can make changes, run the code, and probably go through a few rounds of debugging. Once we've got something that we're happy with, we're going to push it back up to GitHub, this time under our own name rather than under the Allen Institute organization, and then close the loop by requesting that the maintainers of the Allen SDK pull from our copy on GitHub into the master copy. And this gives the maintainers of the Allen SDK a chance to look over our code, to make comments, to ask questions, and for us to address that feedback with additional changes. Okay, so building a review into your workflow can help prevent bad code, it can help catch bugs early, and it also builds familiarity within the team. It still takes work. Someone has to actually sit down and go through the review. But with modern tools, it can be relatively painless. Despite review and our best efforts, bugs do crop up. And when they do, we need to track them down and fix them. This can be tricky because a piece of data might be touched by many different programs on its way from an acquisition rig to publication or analysis. And this is a window into just some of the processing pipelines at the Institute. Each box here represents a separate program, and lines indicate that the outputs of one program are used as inputs by the next. And what this means for us is that if we want to understand the outputs of one program, say the one circled in red, we need to also understand the behavior of each program whose outputs form the inputs to that program, such as the one circled in blue. And not only that, but we don't reinvent the entire history of software development every time we sit down to write some code. We delegate functionality to libraries. And so the behavior of our programs depends on the behavior of those libraries as well. What this boils down to is that our data have history. And in order to make our work reproducible and debuggable, we need to track that history and communicate it to the maintainers of our pipelines as well as to our users. This is, I think, in general, a really hard problem, but some tools exist that make it easier, and I'll run you through an example of how we can track that a particular piece of data was produced by code using a particular library. Okay, so we want to know that we want to associate some data with a library. And not only that, we want to associate it with a particular snapshot of that library's development history. So the first thing that we need is a way to actually identify those snapshots of development history. And software developers solve this problem using version control systems. In this case, the NumPy library uses Git, and each state of the code throughout development is associated with a unique identifier called a commit. For the sake of us humans, individual commits are occasionally tagged as releases, and that gives downstream developers a stable embedded platform to target with their work. And so because the NumPy project and other library developers have used version control for their work, we now have the raw materials that we need to associate our data with the libraries that were used to produce it. So this is a log tracked in our database of a particular run of one of the programs in our pipeline. And using this, we can look up both the data that went in and came out of this run of this program, as well as look at all the libraries in the environment when this program ran, and their versions. And this lets us replicate this environment in order to reproduce the data and to reproduce and investigate bugs. Okay, so we want to be able to reproduce our data and to track down bugs. In order to do that, we need to track the history of our data. We have the tools to do this, and I think version control is a major step towards meeting this goal. But it's not the whole job. We still need to build infrastructure to actually associate our data with the versions of code under control. With that, I'm going to hand you off to Jed, who's going to talk about another important aspect of pipeline software development, which is testing.
Hi. Yeah, so I'm going to talk about how we actually develop a piece of software to run in the pipeline in a way that we know that it is doing what we want it to do, and that as we make changes to it, it will continue to do what we want it to do. So what I have pictured here is sort of an idealized test-driven development cycle, where the first thing we do is gather the requirements for what this piece of software needs to do. That is, we talk with our collaborators, we define what it needs to actually accomplish, and then we define what metrics we have to know that we are succeeding in performing. Then we actually design the software, which is We do some prototyping to figure out exactly how we're going to go about structuring the code. We define all of our inputs and outputs, and then put together the skeleton, but we actually haven't implemented any of the functionality yet. Then we actually develop the tests, so our unit tests, which let us know that the pieces are continuing to work correctly, and then maybe regression and integration tests for more complicated programs. And then at the end of that, we actually write some code. So what this looks like at a very simple level is I write a function definition, and it doesn't do anything. There is no implementation, but I know what my inputs are, and I've documented all of the behavior, and I've actually fully implemented a test that will fail until I have implemented this thing to be correct. So that's like what the ideal development would look like. In reality, it looks a little more like this. We start gathering requirements and we do our design. We write some tests, we start implementing, and someone is like, oh, I actually need this right now. So we put it in the pipeline and then it breaks. And we're like, oh, well, we better add more tests. And then they're like, it doesn't really do what I want. And we kind of like iterate on that until we end up with a thing that works. That process actually makes the testing really important because we need to be able to detect when we push a change that it will that the code will continue to work. And the answer to that is actually test automation called continuous integration. So there are some tools for that. Externally, we use Travis CI and AppVeyor. That allows us to, on push, run all of our tests across all operating systems and maybe against different library versions. Internally, we use Bamboo, and that's just an internal tool, but we have access to internal data for long-running tests or regression tests. At the end of that, after a push, we should get output that looks like this, that says, hey, everything worked on all of the platforms. And if we don't get that, if I have a red X instead of a green check, then I know I need to make some fixes. So that works really great for individuals developing on their own pieces, but for example, MTrain is a service that selects a stimulus script. The stimulus script depends on some library code, and then there's some analysis code that depends on the output of that. Those are actually all developed by different teams. So what that means is if I check in a change to some analysis code and it breaks, well, I'll know that right away, and that's great. But if someone else checks in a change to the library code that maybe moves some data around in that output file that the analysis is looking at, well, I've broken the analysis now, but I actually haven't detected it. The solution to that is chaining builds and basically building integration tests. So either on a schedule or triggered with commits, I can, for any change to any one of these systems, run all of the integration testing, and that way, when the library code is changed, the analysis tests run, and I will find out right away that something went wrong. And that's particularly important for externally facing software where the feedback loop isn't as quick as being able to come to my desk and saying, hey, this isn't working. And so with that, I'll hand off to Nika, who will talk about an external tool.
Hi everyone, my name is Nika, and I'm here to talk about some of the work we have done in our quest to provide open data to the scientific community. I'm not going to talk about the generation or storage of this data, nor the work that's required to make it publicly available. Instead, I would like to provide some of the work we have done to make this data more accessible and useful. So imagine that you're a scientist and you just downloaded some freshly minted bytes. If all you have is this data, how would you begin your work? What does each bit mean? There are so many questions that need to be answered before you can write your first line of code, let alone be productive. In order to give a head start to our data consumers, we use our expertise to provide a suite of software tools for analysis and manipulation. But there's another roadblock to productivity, and that is like these tools, they need to run on a machine with a specific configuration. So we provide our users a template for creating the necessary computational resources for running the analysis tools and accessing the data in the cloud. But sometimes you need to have very powerful machines or a cluster of machines in order to run these tools. So in the case of the workshops run by the Institute, we create the infrastructure for our users. But this is not the end. In order to get over these barriers, we provide these, we create these infrastructures for our users, and then they need to be sustainable. A sustainable system is a system that is reusable, low maintenance, and requires low effort to bring to new users. So for this talk, I'm going to use the infrastructure we use for the Dynamic Brain Workshop as an example. Dynamic Brain Workshop is a workshop that is run by Allen Institute and the University of Washington every summer at Friday Harbor. We bring in about 25 students, and we teach them Python and how to use our analysis tools. Last year, we decided to use the cloud for hosting the data files and the analysis tools. So why did we use the cloud? It's because why don't we just like host the files and ask people to download them? That's because some of these files are so large that they won't fit on a typical machine. So we decided to use Amazon Web Services. And here we would like to thank Amazon Public Data for their support and funding of this project. Amazon Web Services provides cloud-based pay-as-you-go resources. So basically, this is the design that we used for the workshop last year, and I'm not going to go into details, but basically every icon you see here that is in orange or red is a service that is provided by AWS. We use the ones in red for hosting the data files, and the ones in orange were used for accessing the data and running the analysis tools. So we tested this design at the workshop last year after some rounds of internal testing, and we ran into some problems. We ended up with an unbalanced infrastructure, which meant that some of the servers were heavily used while others sat empty. And also, if someone ran a task that was too heavy for a machine and caused the computer to crash, none of these other users were able to use that machine anymore. But even with all these problems, this infrastructure was a success and started to get used in more workshops. But this is when we ran into another problem, sustainability. Basically, before every workshop, a software engineer would have to spend quite a bit of time in setting up the infrastructure. So overall, this project was starting to become quite costly. So we decided to go back and think about a different solution. The next iteration is a web application that allows users to create the necessary resources for accessing the data files and running the analysis tools. This new design included an integration with GitHub. In the previous design, we were creating the usernames and passwords ourselves. This meant that before every workshop, a whole new set of usernames and passwords would have to be created and distributed. This was also very inconvenient for our users because they had no control over their credentials. Creating a good authentication system requires a lot of resources that may not be available. It requires a lot of hours by multiple software engineers. So we decided to integrate an existing system with our application. Also, one other change we made was we simplified the system. We leveraged a new AWS service that simplified the creation of the computing resources. Basically, every service you see here that is in this blue box was replaced with these ones. This new service included a lot of the functionalities that we were trying to recreate with the initial design. So this meant that a lot of the maintenance work has been pushed to AWS. Also, with this design, we were able to provide a computing resource to each user. So this meant that no one is stepping on each other's foot anymore. So we tested this design again this year, and the result was much better. We ended up, there was a lot less maintenance and babysitting by engineers, and a much better experience for our users. As Nick, Niall, and Jet mentioned, software engineering requires a lot of collaboration. And you might even say that it's inherently collaborative, because even an author of a sole software project must collaborate with their future self. I think this quote by Alan Turing sums it up pretty perfectly. I think except that I think he meant to include women as well. We contribute to each other's code and often work together and with other teams to solve problems. We build on top of each other's work, and in order to work, for all of this to work efficiently and cost effectively, it's worthwhile to invest in practices that enable us to build build sustainable products. And at the end, I would like to thank everyone at the Institute, and especially our founder and his vision, who enabled us to make all of this possible. Thank you.
Thanks for that great talk. We have a few minutes for questions. Just raise your hand and a mic will come to you.
Yeah, this is sort of a global question to all of you. What fraction time you spend when you do coding, programming, do you spend writing a first draft compared to what time you spend on debugging? Is it like 1 to 1 or 1 to 10 or 1 to 20, 30?
Yeah, it really depends on how hectic the development cycle is. So that the amount of time spent, if we're able to really gather our requirements correctly the first time and start implementing, very little time is actually spent debugging, and we get to spend almost all of our time just planning and implementing. For most projects, I would say that probably maybe 30% of my time is spent debugging, just based on the way that requirements actually roll in and we discover bugs. I don't know if that's the same for the rest of the team, but about 30%.
I'll also just add that code quality or code reliability is not a binary state. It's a continuum, and I think that reflects the state of the library dependencies of a project that you're trying to develop. I think it's, at least in my experience, one of the major determinants of how much time has to be spent debugging. It may not be a problem with your code base. It may not be a problem in the code base of your dependency. It may be a mismatch of the expectations of what you can rely upon or the development cycle of things you can't control. So a lot of times it's a question of what type of ground you're building on. Like Jed said, if you have the design requirements, if you know where you're trying to get to immediately, I think it's actually a pretty fast loop and it's very efficient. But if it's an uncertain space, if the dependencies are uncertain, and if the eventual use case is critical for example, to be a service that always has uptime, the animal is always trainable in any state, any day, those requirements really inflate the amount of time and effort that have to be spent. If you push me for a number, I'd say 3 to 1.
That was really cool, guys. So you talked a lot about test-driven development, about spending a lot of time on documentation and reviewing code and so on. And all of these things are like undoubtedly useful, but they also suck up extra time. So especially thinking about like documentation and review, right? Which don't necessarily increase the quality. They do increase the quality of the code, absolutely, and it's like a useful thing to do. You should do it, but it's like it's an additional cost, right? So how do you balance that? It's easy to kind of maybe choose some level. Do you revisit that? How much time do you spend doing one versus the other, and how do you sort of choose to make that balance?
That's a good question. I think that, at least what I've found, is that if I don't build review and testing into my regular workflow, then I always end up paying more time later for that work. So I think it's I don't know that I set out an explicit division of time, but rather I just build it into my day-to-day.
You're not asking like 30 other people to review every commit that you make.
No, typically...
It's the extreme version of this.
Yeah.
What actually...
Yeah, typically we just pick a small set of people who are, working within that project for review.
I can also add one more thing, and that's basically there's this idea that code is meant to be read by humans and not computers. So like if someone else has to go back and look at your code and has to spend a lot of time not understanding what's going on, there's a lot of that cost that could be added. So overall, like using these practices and putting them early in the cycle is always more cost beneficial than like just saying it's not possible.
Can I just add one more thing? Also, the first time you do test-driven development or the first time you use code collaboration strategies, you probably will not be very efficient at it. Just the same as the first time you design and implement an experiment, you won't be very efficient at it. But after your 10th or 15th time, it becomes second nature, it becomes very easy and very fast, and then you bend the curve just through your own experience. And additionally, if you do it with awesome collaborators, that experience arc gets bent much, much faster because you have sort of an apprenticeship learning situation. So the first time on your own in a vacuum, I think that there's an argument to be made that it may not tip the cost-benefit analysis for every project. After 10 or 15 rounds, and after paying that cost multiple times, in my experience, it's a no-brainer.
In your projects, you guys often, the BNL project, you get some prototype code from one of our scientific collaborators as the benchmark, or here's a module that already works. What is the one or two things that you will like them to have done by the time they hand this code to you?
Honestly, I think that the best thing to do would be to not develop some prototype code and then hand it off, but instead to start the project collaboratively from the beginning, because that's really all the best practices that we're talking about. So we'll take testing, for instance. If tests are in place for a package of code, then we know that we can make changes to it while having some confidence that we haven't broken bits of it that we're not looking at. But those need to be in place before we make the changes. And so I think that getting everyone on board early is actually the best thing to do for handoffs.
And I'll also throw in another thought on this culture that we've been a part of and that we're sort of evangelizing. It's a lot of fun. You'd really be surprised how much fun you can have talking with your collaborators, designing tests, interacting, and building cool things together. There's intrinsic payoffs as well as bottom line payoffs.
All right, let's thank our informatics team one more time.